Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about matrix operations. Matrix operations. So here we go. Matrix operations. Okay. We're going to talk about three different kinds. The first one we're going to talk about is, and it won't take long, is addition. We'll talk about, well, you know what, we'll go through this in the same order that we did with vectors. So the first one is scalar multiplication. Scalar multiplication. Now, it won't surprise you, but we're going to write it anyway. But think about scalar multiplication for a vector. It just means that every component of the vector is multiplied by the scalar. It's exactly the same for a matrix, and it makes sense in that a matrix is very simply just a series of column vectors. So it's the same thing. So let's write that. So I'm going to just use, we're going to do this by example. So if I have some matrix, let's do this. If I just have C times, I'm just going to give you an example. How about like, ooh, that's not going to work. Oh, you know what? Let's just use a number. We're just going to show you by example. We'll use the number 2, and here we'll have a 3, 4, 5, 6, 7, 8. So scalar multiplication means that every element of the matrix is multiplied by the scalar 2. So this is going to be 6, 8, 10, and it's going to be 12, 14, 16. And that's scalar multiplication. 2. Matrix addition. I'm going to do this for, this is a 2 by 2 example. We'll just do a 2 by 2 example, but let me write this. Matrix addition says that matrices matrices are added component-wise. So let's do it this way. So for example, if you have the A, I, J component of a matrix A, well then you're going to add it with exactly the same component position-wise, I, J of the matrix B. So if I have an example, say I have the matrix A, A, B, C, D, and I want to add to that the matrix of W, X, Y, Z. Well, we add those two together. We add component-wise. So the 1, 1 component in the first matrix plus the 1, 1 component in the second matrix. So we have A plus W. We have the 1, 2 component with the other 1, 2 component. So B plus X, C plus Y, and D plus C. Okay. And that is how we add. there's one more, and that's going to be the real focus for today, and that's matrix multiplication. It's understanding this is really going to be the key to unlocking the subject itself. So let's do this. Matrix multiplication. This is the big one right here, 3. Matrix multiplication. Now, we said, we've already started this process. Do you remember when we started with something like A times the vector x? And we said that what this was is this is, I'm going to write this out, is a linear combination of the columns of A. Now, then what we did is when we solved, now this is where you have to think about how this works together. So then what we did is we solved AX equals B. And how did we do that? Well, we solved that using row operations. By using row operations. And then, so what we did is by using row operations, and let's see, this gets even better, and row operations gave us, row operations were encoded in the elementary matrices. The elementary matrices E. Or we could say E, or the individual ones are E, I, J, and the product of those we just called E. So let's put this together. So what we had is we first learned multiplication of AX equals B. This is a matrix times a vector. Well then what we did is we said the row operations could be encoded by E. And E was multiplied by A. And what we found, or the way we treated this is we said that this was E times A, where I'm going to write it this way. A has column vectors of A1 and A2, and you could have as many columns as you needed. We'll just go out to 3. That's enough to see what was happening. Well, what we did now is we treated this problem now. This was just like, now we've just taken this E like this A. And so we multiplied E by the first column. And then it said, oh, we'll do it again. So we did. And do it again. And so we did. So what we did here is our final result, the new matrix, was E times A1. In other words, it was just the matrix on the left times the vector on the right. Matrix on the left times the vector on the right. So we had EA1. This gave us our new column vector. Then we had EA2 to get our second column vector. And finally EA3, and that gave us our third column vector. Now, what were each of these? This says it's just a linear combination of the columns of E. This is another set of the linear combination of the columns of E, and so on. So here, when we think of matrix multiplication this way, we're thinking of this as this is linear combinations of the column of E. The columns of E. Okay. That was the first approach. Second approach. The second approach was, what is E? E represents row operations. E represents row operations. So let's actually try a specific, or a kind of a semi-specific example. So for example, so this is our first method. Linear combinations of the columns. Linear combinations of columns. Okay. Now, let's think of it the second way. The second way is this. Let's say we had the matrix E21 times A. And we're going to just assume that these are 3 by 3 matrix examples so that you can, these aren't proofs, these are more understanding. Well, what did this do? So what this said is when we did this, the purpose of this, of E21, is it changes row 2 using row 1 by some multiplier. We called it L. So think about that. So in other words, E21 times A. Well, what did it do? We had E21 said we have the first row. I'll write it this way. We have row 1. We had row 1 of E. And maybe there was a row 2 of E21, and we had row 3. Now, we multiplied that by the matrix of A. Now watch this. Well, when we multiply E21 times A, we didn't change anything. There was no change in the first row of A. In other words, it just this, and how did we do that? Well, we took row 1 of E and we multiplied it by A. And we're going to keep track of this now. And what happened here to A? The first row of A, there was no change. Okay, so this matrix does no row operations on the first row of A, nor does it make any row operations on the third row. Oops, that's a no change here. And that was because we had 0, 0, 1. And so row 3 of E21 times A, this created no change at all. But now what happens? When you take row 2 of E21 times A, well, this was a row operation. On A. A row operation on A. And so, wait a minute, what's happening here? Now what are we doing? We're making linear combinations now of the rows of A. That's what a row operation is. So when we think of multiplication this way, what do we have? We have linear combinations. Linear combinations of the rows. This is the key part of the rows of A. Okay? So, one way to think of it, linear combinations of the left matrix, or you can think of it as linear combinations of the rows of the second matrix. Okay? So there's two ways now that we can think about multiplication. Oh, you know what? There's even another way. Let's do this. Think about this. Think if I had, let's do this. Say I have, oh yeah, we'll do it this way. You know, E times, oh, nope. Okay, show you this. So, say I have the matrix A, B, C, D times the matrix, we'll call it like x1, x2. Okay. Well, we've said that this can be written as linear combinations. And we've also said we can just take the result of the dot product of the row with the column. And in other words, so this is row 1 of A dotted with X. And then the next entry here is row 2 of A. Again, dotted with X. Okay, now, think about this though. What if I have the same matrix, A, B, C, and D, and I wanted to multiply it by a matrix x1, x2. Oh, and then maybe we have a y1 and a y2. Well, what have we done? What have we done? Well, this is the answer for the matrix times the first column. We've already learned that. That was the very first thing we've done. So I'm just going to put an arrow. That's the first column, is right there. Well, what happens on the second column? The second column is the same thing. We just apply the same process. So now it's row 1 of A. I guess I'm calling this A. Row 1 of A dotted with this. But what's this? This is the vector of y. And then we reply it again. It's row 2 of A dotted with the vector y again. And so we have our next result. But look at this. This is the more important thing here. If I want the entry 1, 1, then what it was, 1, 1, was the dot product of row 1, column 1. If I wanted the entry for row 1, column 2, it's the dot product of 1, 2. Row 1, column 2. Okay, so let's try a general example. Say I had the A times B equals C. Now we're going to fill in, use some notation as we go here. Let's say A looks something like this, and B maybe looks like this, and oh, and you know what? I want C, let's do C3/5. No, that's a lot. No, that's okay. How about the C3/5? Who knows? It's somewhere in there. So here's what I would do. I would take row 3. So row 3 of A, well, that's a row 3, column 1, and there's going to be an A, 3, 2, and an A, 3, 3. Maybe that's enough. We could take it out. I'm going to do it this way. How about an A, row 3, out to the nth column, times the 5th column, or dotted with. So this is going to be B. We're in the first row, but now we're in the 5th column. And then the second B would be in the 2nd row, but still in the 5th column. And we would continue this process. So this A with this B, this A with this B, and you'd continue that all the way out. Every single one has to match. That means B has to have n rows. So this is going to be B, column 5. Look at what we've got. So what do we have? Here, A, we usually say has m rows. And it has n columns. So B, in order for this multiplication to happen, the number of columns of A has to match the rows of B. So we have n rows of B. And how many are n columns? I'm sorry, n rows. And usually what we would do is we would say that we have, maybe something. Oh yeah, rows aren't that way. Those are columns. There's n rows. Those are over here. Goodness gracious. And we would have P, who knows how many. You can have as many as you want, P columns. Okay, so let's see, C3/5. So C3/5, well, it's A31 times B15 plus it's A32 times B25 plus, and then we would keep doing this. We'd keep doing this until we come out to our last element, which is A, row 3, column n, times B, which is now row n, still column 5. Well, this comes from, so what we've done is we've taken the dot product of row 3 with column 5. And we have a notation for this. Look at this. Notice that these inside numbers here, they always match. So what we do is we often write this as the summation of A, 3K, B, K, 5, and K has to go from 1 up to n. Okay? And it's row 3 dotted column, row 3 of A. I should be specific there, huh? Column 5 of B. And that is how you find a single element of a matrix. Okay, here's the best part. We've looked at 3 perspectives. You need to remember that all these give you the exact same result. That has to in order to work. It's not that's so important. Most of our individual calculations are going to be done this way, but as we move on, you want to think about where the entries are coming from. Were they linear combinations of columns? Were they linear combinations of rows? Was it a single entry? Okay, I have one more for you. And I think we have just enough space. I'm going to go back down here to a little erasing. So let's go back to the start. Back here. And I have a fourth way to show you. Fourth way to look at matrix multiplication. Oh, actually, let's go back to that example for a moment. I want to show you one last piece. Or actually, we'll start right here. I'm going to continue. So what we said there was when we had A times B equals C. Oftentimes you'll see it written like this. A was an M by N matrix. It was multiplied by B, which is an N by P matrix. And the result, C, is going to be an M by P. An M by P matrix. Okay? So the key thing, matrix multiplication, it just does not make sense. It does not make sense if this number here, the columns of A, has to match the rows of B. So these always have to match. Okay, so if they don't match, then there's just no multiplication. All right, let's look at one more example, one more perspective. Let's try this. How about if we had the vector 1, 2, 3. I'm going to write it. Actually, I'm going to write it over here. So look, this will work better. Okay, so 1, 2, 3, and let's multiply that by, let's do this. How about -1, 4? That'll work. Now, remember, we said over here that if I want, oh wait, you know what? This is just a column vector, but a column vector is still a matrix. It's a 3 rows, 1 column. They would call this a row matrix. There's only just a single row, but there's 1 row and 1 row by 2 columns. So notice this. These match, the ones match inside. So it tells us that our result is going to be a 3 by 2 matrix, a 3 by 2 matrix. So let's put that up here. Well, we know that it's row 1 dotted with column 1 to get the first entry. So 1 times -1 is -1. Then it's going to be row 2 dotted with column 1, so that's going to be -2. Continuing, that's a -3. And then we're going to take 1 times 4, 2 times 4, 3 times 4. Okay. Ooh, let's try another one. Watch this. How about we take maybe like 5, 6, 7. And let's multiply this one. Let's multiply this one by, how about -3 and 11. I like 11. All right. Well, pause the camera. Give that a quick shot. And then we're going to write the answer up here. So try it yourself first. Otherwise, let's see if we get the same results. I'm going to get a -15, a -18, 18 minus 21. And then I'm going to get a 55, 66, and a 77. Okay. Now, here's the interesting part. What if I gave you this? What if I gave you the matrix of 1, 2, 3 in the first column, 5, 6, 7 in the second column, times the matrix of -1, 4, -3, 11. Okay. Now, we're going to write this out. We're going to write this out so that we can see what's happening here. Well, let's just do this, the dot product. So the dot product of the row with the first column will give me my first entry. So I'm going to have a -1, -5, minus 15. -1, -15. And then my next entry will be -2, -18. -2, -18. And then I'm going to have a -3, -21. -3, -21. And I know you probably just want to write -16 and -20 and -24. And you can do that. That's fine. But you'd miss the point. So 1 times 4 plus 55. So 4 plus 55. 2 times, that's an 8 plus 66. And finally, I have a 12 plus 77. Look at this. Look at what we just could have done. I could have just, by putting these columns to get into a matrix, and these rows into a matrix, and leaving the order the same, look at what I could have done. I could have very simply added this first matrix plus the second matrix and gotten the same result. So what does that tell us? What does that tell us? Well, it tells us this. It says that if we have some matrix, we have it maybe column 1 and column 2, and who knows how many. Maybe we have up to column n, and I multiply it by some matrix here, and it has like, maybe it has, we'll use the same notation, row 1, and then there's a row 2, and a row n. Well, I could also find the answer by taking, oops, that's a column 1. I could take column 1, that's not a dot, this is just times row 1. And that would give me, this is an entire matrix. And I could take and add that to the matrix of column 2 times row 2. Plus, I could take all of that out. I would have n matrices, column n times row n, add them all of these n matrices together, and I could again get the same result. And that is the fourth and final way to look at matrix multiplication. Thanks for watching.